Okay, it should be recording. Now let me just check the sound, make sure that it's okay. Yeah, it looks fine. Okay, I did put up some notes. You have all the assignments. What we're going to cover today is sections 5 and 6. I'm skipping for now. You notice that if you look at the notes, previously we covered sections 1, 2, and 3. You notice that I skipped section 4. And section 4 is on databases, and I may spend a little bit of time on Monday covering just a little bit about databases. That's actually a fairly big topic, and the only thing I want to do is maybe give you an idea and just do a little bit. What I decided to do today was to talk about a topic that's perhaps more relevant, and that is about XML parsing. And also, that's section 8.5, and 8.6 deals with some public databases that are available. So I'd like to do a little bit of that today. Guess I should have shut this from last time. So I'm going to go into 523 now and look at the notes in Chapter 8. By the way, the one chapter that I didn't cover too much is Chapter 9. Looks at, I talked a little bit about a couple things, but basically Chapter 9 is on debugging. So if you write bigger projects, you're going to need more sophisticated ways of debugging your code. I believe I mentioned one thing, or a few things, but basically the debugging, if you start doing more R coding, you might want to take a look at that chapter. So here's section 8, and let me set that as the working directory. Actually, I'm going to clear this off. Let's see if I'm also going to clear this. Okay. Perhaps there would be some utility to be looking at the environment as we execute some of this. First of all, I'm going to knit this, and there are actually quite a few sections here, so it'll take just a little bit of time. There are a few areas that don't run because of changes in the code that have taken place since the book was written. And this is taking a while. Are a bunch of you also doing this? This maybe wasn't a good idea. Okay. Okay. So I'm going to talk about 8.5 on XML, and we'll sort of flip back and forth. There's a new book coming out in first part of the year called Data and Web Technologies, and a lot of the web technologies were written by Duncan Temple Lang, and in fact he's the co-author of this book. And I think that he probably did most of the coding, and Deborah Nolan is the co-author, and she's a pretty good writer. So I'm hoping that it's a fairly good book in terms of both the code that underlies the book as well as the actual examples and illustrations relating to this. And one of the things that will be in that book is, XML parsing. So what is XML? XML is extensible markup language. So if you think about what renders this page and what underlies the web, it's HTML, or hypertext markup language. And HTML, unfortunately, got up to a fairly bad start in one regard. There were two problems that happened back in the early days. Um, you may recall that Netscape was kind of the charging force back in the 90s for the web and HTML. And what happened was there were a couple things that happened. One is that Microsoft got into the game a little late, and when they did, they started putting in proprietary things into HTML, which sort of counter to the open web. And then Netscape started doing the same thing to counter that. So you started having web pages that were incompatible with different browsers. Now, that's still true to a little bit today, and that's not so much because the standard is incompatible, because now there's a standards organizations in the World Wide Web Consortium, or the W3 Consortium. And so there's a standard, what's currently HTML5, which is pretty advanced for doing hypertext markup language. The problem is there are a lot of sloppy people that create web pages. Typically, you have elements, and typically you have a beginning and an ending for each element. And so people would leave off the end tag, and there were lots of things that created problems with HTML. Of course, you know, if you use something like BBEdit, for example, you can test your HTML code against not only, you know, does it meet the standards, but you can actually test and see how it runs on multiple types of browsers. So that's one of the reasons I use BBEdit. That's actually, you know, when I go in and create this page, I do everything in HTML using BBEdit. It's very good for doing web development. Unfortunately, for the average person, you know, if you come to the university, they'll say, okay, this is this program we want you to use, and it's a graphically based. It lets you design web pages graphically, which on the surface, it seems like, oh, this is great. You know, it's like Word. Well, it is. Unfortunately, it is like Word. It's graphical, and therefore it creates lots of excess code. It's sloppy, and so, you know, as a user for us, what do we want to do? Well, we actually, suppose you want to scrape the web. So you want to go out and you want to take a page and you want to be able to manipulate that page in terms of the elements underlying the page. And so if the page has all this extraneous stuff in it that's not needed, or if it's has lots of errors in it, but it still may render, because what happens is browsers sort of expect people to make mistakes, and they're sort of forgiving of mistakes in the sense that if you leave off the end tag, it will still probably render okay. Like you have a paragraph and an end paragraph, and you put those in angular brackets, and so you got like a P and a /P in angular brackets. That's stop paragraph, and so forth. And so you have all these tags, but most browsers will render it even if it's not done correctly, as long as it's not too incorrect. But for us, that we actually treat the web page as data, and we want to parse it and pull information out of the web page, if it's sloppily done, it creates problems. You know, because what we're going to do is treat it as data, and we're going to scrape information out of it. You see, that's like what the NSA does, right? But we're going to do it not for nefarious reasons. We're going to do it to get information. Now, XML is usually better specified, but HTML5 is technically a type of XML. So, at any rate, we're going to use web pages as data, or in our case, as XML documents. And if you think, one of the things you should realize is that an XML document or an HTML5 document is actually like a tree with nodes and branches down. In other words, it's sort of like a list in R, where each element could be a list. It's like a list where each element is a list, and then those elements could contain lists, and so forth. So it's called a recursive data structure of lists. And you can actually recursively go down through the list, but that's actually the way the document is organized. It's like a tree, an inverted tree where the trunk's up here and then it inverts out. And so you can recursively go down through the whole tree. And so you can think of it as nodes branching off other nodes. And you can recursively go down through the whole tree and search it, for example. Or you could search for certain types of tags, and then you could extract the elements from those tags. So that's the way you conceptually think of an XML document, or for that matter, an HTML5 document. It's like a recursive structure of list that you can go down through. That's sort of what it's like. So there's a package called the XML package, and the idea is that we can process each element of a document by specialized functions, which are typically called handlers. Now, if you think of this as a tree, and actually you can also think of a computer program as a tree, and so we need to parse this tree to get the information out of it. And there are two ways that we can parse. One is called DOM, the data object model. And we can parse it with a function called XML tree parse. This function right here, XML tree parse, is a function we can use to parse the actual document. And it basically saves the results back into the tree. So one of the things you could do is have a handler that replaces nodes by null, which effectively means that you've removed parts of the tree. And so you've sort of pruned the tree in various ways, and you're looking at a subdocument in effect. So an XML document is highly structured, and there's a data definition that will define the structure. You can define your own elements. In HTML5, the elements are defined for you. So, for example, if I go into BB Edit and I go in and if I go in and create a new HTML document, and by default it's going to create an HTML5, but I could actually create lots of others going back to HTML 4.01, I guess is the lowest. XHTML is sort of extensible hypertext markup language, but if I just created a document, that's the basic structure. Here's a tag and here's the end tag. So that says begin the HTML and end it, and then you have a head section which defines certain things, and then the actual thing you see on the web page is in here. And so if I went in here to the markup and I said, okay, I would like, you can do forms, you can do lists. So if you'd say, okay, I would like an unordered list, I could do this. And so UL is a tag, meaning unordered list. And then I have LI is the item. And typically if I have an unordered list, I would have multiple items. So I could create I could go in and I could create with list. I could go in and create another list item, and so that would be bulleted points. When you think about having bulleted points, if I did an ordered one, it would have numbers or some sort of way, A, B, C, D. That you can actually specify this. So here, notice that this is hierarchically embedded within body. So you can think of body, and then you can think of these other elements, and then this is embedded. The items are actually, whoops, well, I didn't mean to do that. I mean to undo the paste. In other words, these tags, and notice that I have in brackets LI, and then that's the beginning tag, and the end tag is the same thing with a slash in front of it. That's the end tag. And so this is the way you can easily, create something. So if for example, you wanted to, if you wanted to sort of look at the web page for the course schedule, then you could, I can show it to you. So if I go in if I go into HTML public, and if I look at courses, and if I look at this course, and if I look at the schedule page, whoops, didn't mean to do that. What I meant to do was take that and then open it with BBEdit. So this is actually the document underlying. Notice that I have I have lists and so forth. I actually have a table structure. So here's the body, here's the head, and that's just the HTML document that underlies the web page that you've been looking at all along. This this page right here. It's pretty simple, actually. Okay, so but suppose you had a web page that had information in it, and you wanted to suck that information out into an R data structure and analyze it, either using text processing, or perhaps using regular expressions, or perhaps it's data, and you extract the data out, and you want to put it into a data frame ultimately, and then do statistical analysis. There's lots of data out there that's embedded in web pages. So this is, did I shut that? Anyway, that's sort of the basic idea of, behind XML documents. So in the case that I was looking at was actually an HTML document. Now, one of the things that HTML5 has become very rich, and one of the goals was to not only make it rich in terms of the structure of the document, but it became rich in terms of the underlying media capabilities. And so it used to be that if you wanted to do rich media, you had to use something like Adobe Flash. Unfortunately, Adobe Flash, there were a couple problems with Adobe Flash, besides the fact that it was unstable and caused people's browsers to crash. It was terrible on mobile devices. It was a resource hog, and if you ran a lot of Flash on a mobile device, your battery it was very inefficient. And that's why Steve Jobs always refused to put it on the iPhone, because it killed the battery life very quickly, plus it was unstable. And HTML5 was becoming rich enough, and it's a standard, not a proprietary format of Adobe. So HTML5 is a standard, and the rich media now can do about everything you can do in Adobe format, but you can do it using standards, including rich media. And so that's why Adobe abandoned Flash on mobile devices, because they can never figure out how to get it efficient. And so they've orphaned it, although it's still a run on some platforms. It's no longer being developed. And so, although it still runs on a desktop. But again, a lot of people now are converting to HTML5 with rich media. And that's good because it's a standard and not proprietary. So at any rate, and you might think that images on the web are not susceptible to statistical analyses, and nothing could be further from the truth. You can pull off images from the web, and you can actually analyze them statistically, and I have some books that do this. You can apply your own filters, you can transform images, and so forth. But you can also do pattern recognition. So if you had images that were taken of people in Grand Central Station, and you wanted to try to identify people, and you had a database that had these people in it, or at least it was a criminal database, in principle, you could pull these images in, and if you had access to that database, which you won't, but if you did, and believe me, some people do, then you could actually compare these pictures to this database for identification purposes. You realize in the Boston bombings with the race, they actually identified the people pretty quickly. And the question is, can it be predictive to identify in advance? But at any rate, besides DOM actually brings the whole document into memory, and it works on the whole data structure at once, or the whole content structure at once. Which means that if you have a huge file, it would have to bring it all into memory, and that may not be the most efficient way to do it. So there's another way of parsing called SAX. And SAX actually does it on the fly. In other words, it does what's called event parsing. It goes through the document, sort of linearly through the document, and it parses it as it comes to stuff. And it's called event parsing. And there's a function called XML Event Force, which is used for that. So there are two ways you can parse. If you have a very small document, it doesn't really matter. You can bring the whole thing in. If you have a very large document, it does matter, and you probably want to use SAX parsing. So at any rate, so we have, so we're going to have an example here where we have an XML file in a particular database, and this happens to be in the RBioInf package. So there's a package that has a particular file in it, and what we want to do is parse it. And this particular package is actually in the system file. It's in this particular package, and the name of the structure we're going to get is this yeast data. There's a yeast file in there. It's an XML file, and so we're going to extract it from. We're going to extract that document from the package, and we're going to name it as yeast.fn. Okay, so let's take a look. Let's go over here and take a look now. Where did I get? Down here, I think. So first of all, I'm going to do this, which extracts the document yeast.fn. Well, I'm calling it yeast.fn. It extracts it from the BioInf package. The actual name of the file is yeast_small-01 docs.xml. That's actually the name of the file. And so internally, we've called it yeast.fn. And we now, in order to do anything, we have to load the package XML. And then what we're going to do is we're going to actually parse this document, what we'll call, well, the tree version of this, when we actually parsed it using the XML parser, is called yeast, INTACT. So that's what we named it. And so now what we're going to do is we're going to, yeah, I didn't run that yet. So let's do that next. Okay. So we should be able to look at the class. Was that a small? And this says it's an XML document that inherits from XML abstract document. So there's this abstract document concept, and then we have inheriting from it is XML document. So that's the class of this. Now what I'm going to do is I'm going to find a root. Remember I said the XML DOM tree has a root. And what we're going to do is we're going to look at the root of it, and we're going to look at the namespace. In other words, the problem is we talked about namespaces previously. For these documents, we typically need to know the namespace of the document. So I'm going to get, there's something called XML namespace definitions. So NS for namespace of Y are the namespace definitions. There are also some default namespaces. And let's see. Well, let's see. Let's do a few things. So NSY, here's the URL that's sort of built in for this particular document. And then, let's see, That's a URI, actually. There are actually two of them. There's this. Notice that we're in this first element. And then there's actually a website, which is the XML schema, which defines the XML document. Okay, so this may or may not be useful for you, but at any rate, later on we're going to need to know the namespace. And if you have a package and you have to know what the namespaces are so that you don't have conflicts between names from different packages. If I write a package, I can name something whatever, and if you write another package and you name it the same thing as I name it, then which one gets used by R? Well, it's up in the air, whichever one gets loaded in the search path first. So if you load a package after my package and you want my functions, let's say, my functions are masked by this function afterwards, you won't get my functions. You'll get something else. And so the namespace makes you say, okay, this is the namespace for this package, and therefore if I specify the name of that namespace, you will get the correct function. And we talked about this briefly, but what we're doing here is just getting the namespaces to be sure that, everything is okay. Now notice down here, when it gives this, for example, you can look at these. I left this open because you can actually look at these R objects that are created. And I don't know how big this is. This maybe was not a good idea. It wasn't a good idea. It's 81.6 megabytes. I should have noticed that. I need a stop sign right here. It may not let me, maybe it's going to let me do something. Let's see if it lets me do something. So if I look at the length, perhaps I should have done this first. If I look at the length, oh, not good. I may have to kill this. Yeah, when we're actually writing software that does stuff like this, we actually load it incrementally, so that we'll load part of it, and then the user can decide if they want to load more, rather than getting stuck and trying to load this huge amount. Let's see, did it stop? I don't know if it's still not operating here. I'm going to have to kill this, and I'm going to kill this and go out. What now?
Something came up.
What now? Oh, did it come down? Oh, error. But it's, oh, okay. It actually never showed these results, and maybe there's a maximum length you can have. I don't know, but if there is, it shouldn't have let you even do it. It should have stopped you, or it should have given the first 10 and then cut it off. So at any rate, well, let's see if we're still going. The length of the length is it's a list of length too, the NSY, and you can see here that it corresponds to the yeast. Let's see. Okay, here it is giving 3 dots, so it's not. Let's see if I can do this. Yeah, this is not so long, but this one is not so long, the NSY. But yeah, I should have noticed that this one is very big. It does tell you. That's good. I should have looked. But at any rate, now one of the things you can do is you can extract. If I do sapply, and notice NSY was a list of length too. So if I do sapply, and I'm looking down at the, I'm going down 2 levels in effect to actually get the values, then these are the two values that correspond to the namespaces. That was the first one I mentioned, and then this address was the second one. Okay. So let's, first of all, we're going to talk about DOM parsing, and then we'll talk about SAX parsing. So suppose you're not interested in all the content of the file. And so what you might do is define a function. What does this function do? Can anyone tell me? If I apply this function to an argument x, what does it do? It replaces it by null. So that's just a little function that replaces it returns null. Well, what happens if I have this XML tree parse for yeast, and then what this says that I have handlers, this tree structure has tags, and some of the tags are called sequence, some of them are called primary references, and what we're going to do is change all of these to nulls. So in essence, if I have a tag in my XML document called sequence, it will replace that information by nothing, by null. Which means that if you think of it as a tree, now think of it as nodes, and ultimately you get content. Like if you have a list, you get actually the content for the elements of the list. If you have an unordered list, you get the content at some terminal node. And so if I replace that by null, it would be replacing the elements of the list by nothing. It's going to shorten the document. In essence, you've put a filter on that you've filtered certain parts of your document and replaced them by nothing. So if you take a big document, you can actually make it much smaller. If you think of the document as a tree structure, you're putting nulls in various places in the tree, and that means any subtree is null, any sub-component. If you have branching down from that, once you put null, everything below it is null. So if I do this yeast, I'm going to be replacing certain parts of this document. I'm doing this parsing. I'm going to replace certain parts of it by null. Let's see. What did I do? I don't know if something messed up because of... let me see if this runs. Yeah. Did I change something in this? I don't know if I did or not. I'm afraid I messed something up. I'm going to just go completely out and come back in and see what happens. Because this did run, unless I accidentally typed something, which is possible. Okay. I wish they'd go back to the default, but they don't. I mean, I wish they'd go back to where you left off. So let's see if this works. Clear the console just so I get a... sorry about this. Okay, I'm just going to start over and see where we got get. That was a little faster. Something's wrong here with that equal sign. Something's left. Something got screwed up here when I was copying. I can see it's messed up. Mm-hmm. Let's see. This had gotten zeroed out. I mean, for some reason. Let's see if this works. Yeah, okay. Now, quietly, we have nulled out part of this document. So you want to see how much? Well, this was the original size, object size of yeast intact. That was where I didn't null out a bunch of stuff. And that's how big it is. And what now that yeast 2 is the nulled out part. You notice it's a lot smaller. It's only it's about a fourth the size. So about 3/4 of it, the document we nulled out. And you might want to do that. There are various reasons why you may want to do that, because on a particular document, you can have tags that corresponds to all kinds of stuff, but you may not be interested in a lot of them. I don't know. Maybe that sequence was actually referring to sequence data. If you're not interested in the sequence data, that may be quite big. You can null that out. So that's what we're doing. These handlers, I'm applying the null function to these. These actually represent tags in the XML. Just like in HTML5, you have a paragraph tag, you have a UL tag, and so forth. In an XML document, you're actually using it as a storage mechanism, and you actually define your own tags. And then you actually use what's called a data definition document that tells you what those tags mean and what the relationships of the tags are relative to each other. And so you specify the structure of your own document, and then you fill it in with data. And so we're saying that there's a tag called sequence and a tag called primary reference, and then the secondary reference, and then the names. All 4 of those tags we are nulling out. So any information in those tags or the subtree below it gets nulled out. So now, by default, when you do the XML tree parse, it stores the document as an R object. And so it might be that you actually want to store it as an XML document internally. So in other words, when you do the parsing, it takes this tree structure and it actually saves it in an internal form called XML document. That's an internal form to R. And then we can apply different R functions to it. But it may happen that you want to actually store it like an XML document. And so if you actually use that option, use internal nodes equals true, it actually saves it as an XML document in a format that's more akin to the regular XML document. And what this allows you to do is there is a language called XPath. And XPath is a language that you can run from the Unix command line that lets you do some of the same stuff we're doing here, but not in R. It lets you do it in this language, this XPath language. And the XPath is all caps, X-P-A-T-H, all in caps. It's a language, and in my other course I actually taught this language a bit, how you could take an XML document and use this language to extract information from it. So if you wanted to use this language, but use it within R, you save it as a regular parsed XML document, but in XML format. And then I can run XML parse tree, but I'm using the XML format. And if I do that, I'll call that use 3. And then what you can do is this get node set is actually an XPath type command, and it actually lets you, in this particular thing, it gets the attribute list. And that NS means namespace, and this is where we need the namespace for the document. And so the namespaces we had defined previously, and so it's going to use the correct namespaces for this document. So if I do this, and then look at the length of X, this has 10. And so this rather cryptic command here with the double slashes that is part of the XPath language. And I'm not going to go into that very much, but I'm saying it so if someone talks about XPath and that's the way they extract information from XML documents, you'll at least have some idea about what they're talking about. For me, I find it's much more convenient to do all this inside R, because then once I get the information, then I can go right into my text processing functions, or my data. If it's data, I can go directly into my data functions to analyze things. So I can do it all in one nice environment. So for me, it's much nicer to do it directly within R. Now, having said that, one of the problems I've experienced in the past is that the XML package was not completely stable. I think that problem is being fixed now, particularly since they're writing a book on this web technologies, and the XML package is like a key component of that book. So I'm assuming that Duncan is going to make that package extremely stable. So I think it's going to be a lot better as we go forward. So at any rate. So now suppose we want to find all protein-protein interactions, and this data actually has that. And so, you know, what we could do then is this get node set. I could search for the interaction detect method, and I could actually go in and try to get the protein-protein interactions, which I didn't do the full thing. And then it should have done it. And then I can use XML, and it turns out that all the methods are what are called two hybrid methods for getting these protein-protein interactions. And suppose then you want to get the name of the organism you're dealing with. And so again, there's a tag called host organism. That's a tag in the XML document. Now the problem is you have to be able to understand what the tags are and what they look like. And there's a way to sort of extract all the possible tags. And so, you know, as a biologist, say, you would have to know that what the different tags are and what they meant. So it's pretty clear. Usually the XML tags are very descriptive. So if you see a tag that says host organisms, well, that pretty well describes what you're getting. So a lot of times you try to design tags in your XML document that's descriptive of what the tags represent. So so here we can click, and I need to finish it, and then we can map. XML value actually gets the value. You have a tag, like you begin an item and you end the item, and you have content in the middle, which I showed you before. If you have an unordered list, you have in brackets UL, and then you end up with /UL, and then for each items you have brackets LI and end LI, and in the middle you actually have what the items are going to show up on the screen. Your unordered, the items with the bullet points, right? Well, the XML value actually pulls out that middle part. It's the real content that you're interested in. So the paradigm we've been using is we've been getting X4, which gets the node set, and then we pull the content out of the node set. So we're going to get all tags that are called host organisms. In this case, there's actually only one. But we're going to get tags that are called host organisms, and then we're going to use XML value to actually get the content. So when I do this, this would tell you that this is in Latin, that is the host name of the organism we're dealing with. So this may seem rather obscure to you, but I can assure you that it's extremely important. You know, because there's huge amounts of, particularly there's huge amounts of biological data out on the web in these databases. A lot of them are in XML format. Others are in databases. It depends how it's organized. But XML is still very common, and so if you don't know how to extract information out of these files, then you're not going to be doing much if you're a biologist, let's say, or if you're a bioinformaticist. At any rate, so Now we're going to go, what we're going to do here is we're going to look at an interactor list and an interaction list. Now an interaction list are the elements that are doing the interaction, and then we can actually determine the interactions. Now these might be, for example, the interactors might be proteins, and then the interactions may be the protein-protein interactions, how the proteins interact with each other. So if you were looking at interactors, it might be a list of proteins, whereas the interactions would be which proteins interact with which other proteins. And that actually forms a graph, which might be directed or perhaps not directed graph. So, this is the interactors, and I can look at the interactors, and it turns out there are 503 interactors. So if those proteins, it would be like 503 proteins. The interactions would be, well, I commented that out, which must mean that if you actually look at this, it could take some time. Well, it means that it's a lot of output. So I commented that out, but you can look at it if you want. Now here's the interaction list, and then we can look at the length of it, and it's 524. So there are 503 interactors, like proteins, and the actual number of interactions is 500. In other words, not every possible protein interacts with every other protein, because if that would be the case, you'd have a huge number of interactions. So the ones that actually interact, there are actually 524, which is not a small number, but, and again, I commented out that, so, okay. Now, it turns out that there is a function, believe it or not, you see this apply function that we've used in a lot of contexts. There's actually what's called an XPath apply. It's an apply function that gets you both the interactors and the interactions all at once. And so if I execute this, then that will actually, that's equivalent to doing it in 2 steps up here, where first of all I said get node set, and then I had to map it. Then I had to map it with the XML value. So I had to do this second step here, which I blanked out, but there's an example of it up here where the list is shorter. So that sort of combines it into one step. Okay. So basically, if you have a DOM tree, which is a document that you can either bring it into R as an R object, or you can actually bring it in more like the original XML object. If you bring it in an XML object, you have to use these XPath type functions. There still are functions, although you could do it in Unix with the corresponding functions in the XPath language. So what I want to look at now is the other way called event parsing, which is the SAX method. This is an event parsing method. And so we want to consider an XML document, but now we're going to parse it in a different strategy. And so, and typically here, that we have handlers, and we actually, you may wonder, well, we learned about environments a while back, and we'd never used environments very much. Turns out now we have to. Because these handlers can change things or modify things in the data structure, but we have to save it. To save the results so you have access to them, you actually have to create an environment. So let me, so what we're going to do here is I'm going to define a function. ENTSH prints the name of the element and saves the values of the attributes of these elements. So elements have attributes, so we're going to actually save the values of the attributes. So I'm going to define a function here which has 2 arguments, the name and the attributes. So the name are corresponding to an element, and the attributes are the in the R sense of attributes. They're the attributes of the element. And so what we're going to do is print out the name, and then we're going to have two attributes in this case, level and two attributes, level and minor version. Those are attributes associated with name, and ultimately, well, I'm going to define that as a function. And then I'm going to create a new environment I'll call E2, and initially I'm going to set these two attributes to be null. So E2 $level says, okay, we have level within the environment E2, and I'm going to just define it as null, and then minor version I'm going to define null. And then I'm going to associate this function with that environment E2. Now, why do we want to do that? Well, you might then want to go in, if you actually have a particular element and the attributes, if you now execute this, it will save the results where this actually is saving levels within this environment. And that environment is going to stick around, and therefore you can extract the information from that environment. This is a little sophisticated. If you don't understand environments, you probably don't understand this. But as I said, when we're extracting the information, we need a place we can keep it that doesn't disappear. And so we're going to create this environment, and then we're going to initially we set the variables in that environment equal to null. But then if we apply it to a particular element, and that element has attributes, in this case, if the attributes are level and minor version, then they will actually get saved in that environment, and then you could extract that information from the environment. That environment is associated with the function ENTSH. Okay. Now the next handler will extract the taxonomic ID and count the number of interactions. And so what we have the name and attributes, and we have a tax ID, and then we have the attributes associated with tax ID. So that H, I think, stands for host organism. And so I get a new environment, E3, and then I'm going to create a variable associated with that environment, tax ID, which initially is null. And then again, I say, okay, I want that environment associated with this function. Okay. And so now if I actually run this function, which simply increases it by, that actually increases the number of interactions by 1. It just takes the number of interactions and increases it by 1. Then if I look at the number of interactions, and I can associate, again, I can associate this function with E3 too. Okay. So how does this work? If I have XML Event Force and I take the use function, and now what I'm going to do is take these two functions we just created for this particular file we've been dealing with. So we had created these two functions and associated an environment with them. And so I'm going to have an entry set defined as ENTSH, and a host organism is HORG, and interaction is HNT. Hopefully I defined all these. So what I'm going to do is I'm now going to parse it, I'm going to call that S1, and now I'm going to look at the environments for S1 for level text ID and the number of interactions. So if I do this, then there are two levels. The taxonomics ID is that, and then the number of interactions is 503. Is that what we had before? Yeah, that was the number. Oh, looks like it's getting a number of it's a number of interactors. I'm sorry, not interactions. Yeah, This is the number of interactors, which is 503. So that was getting the same information, or at least some of the same information, using SACS parsing or event parsing. So if you actually had to work with these databases all the time, you'd probably get good at it. You'd either get good at it or you'd give up. But okay. Okay, we have a little bit more time. So what about parsing HTML? And as I said, it's a little bit dangerous to do because people tend to be sloppy. And so if you think that, it's almost always true if you have an XML document, particularly if it's a curated document that's in these national databases, they're going to be highly structured, and you're not likely to have errors. If you go out and pull a web page off the web by random and you say, I'm going to parse it, it's a fun thing to do. But a lot of times people are sloppy when they create the XML pages, so you can't guarantee this is going to work. This is sometimes called web scraping or screen scraping. So you can suck in, and you know, most browsers have an inspector. So, for example, if I can remember where it is. So if you do a new window and say you look at our course page, so if you looked at this page, and then I'm trying to remember, I think it's over here. Show Web Inspector. Okay, that shows the overall structure, but and sort of interacting with this. In other words, you usually can inspect these types. Notice what I'm doing over here, it's actually moving the cursor over there. So if you had a bigger screen, you could actually sort of see it interact. So again, you get into the actual, you can see it's a tree structure. You see how it's hierarchically coming in? So you can see that, you know, I keep breaking it down in this tree structure. So you could actually go into any web page and do this. And you'd quickly find out whether or not it's a well-structured page. But I'm just taking our page for the syllabus, and this is what it looks like internally. Now the problem is that if you use one of these graphics things to create your web pages, you get all kinds of junk that you're not interested in. And one of the reasons I like BBEdit is it's very clean. You don't get junk. And BBEdit, if you look at BBEdit, which is a particularly good environment, you actually have all these utilities for checking. And so there's a lot of ways that you can preview. You know, you can preview in BBEdit, or you can preview. I don't know if you can see this, but this says I can preview in CyberDuck, Firefox, Google Chrome, Steam Clip, Safari, TechLive, VLC. So in other words, I can actually check it in all these different browsers from within BBEdit, and it will tell me if there's any error associated with any of those browsers. Now, most people don't do that, and therefore you find things that render incorrectly in certain browsers because they haven't checked it. And anyway, getting back to this, so we can actually, there's something called HTML tree parse, and so if you go into the Bioconductor website, bioconductor.org, and they have when you run rcommand check, you did rcommand build, there's an rcommand check which actually checks your files. Well, that's actually, all the results are posted on the Bioconductor website, and I can go in and find out what happened with all the packages in Bioconductor. So if I get the URL, what I'm going to do here is get the URL for all these check files in Bioconductor, and then I'm going to parse that files using internal nodes, and then I'm going to look at its class, and it's an HTML internal document, its class. And now if we want to, now suppose we want to find all the packages. So if we find the packages and we look at the length, it turns out there are 4,243 packages. Okay. And let's see. This actually looks at a subset. And again, this is using this XPath language, so I'm not going to go into too much detail here, but you can Google it if you want. This looks at a subset of the packages that is sort of nested within others, and it's 261, which is, and here are the first 10. Here are the first 10. Bioconductor is huge. There are a huge number of packages in Bioconductor. I don't think this, not sure this works. Oh, it did. Yeah, but at any rate. Okay, for the last few minutes, I want to talk about some of the resources on the web. One of the ones, if you're in a med school, you're going to be familiar with PubMed. Essentially, all papers. If you have an NSF grant, and you want to kind of get credit for grant, if you want to get credit for papers you write, you have to run it through PubMed. So PubMed is this huge repository of all the papers published from all the journals that are medically related. It's a huge number of journals. You can pull out the abstracts, for example. You can search in all these very sophisticated ways. So this is a part of the National Library of Medicine, the NLM, web services, and you can have tools that you can get a lot of information. There's a package called Annotate in Bioconductor that allows you to go in and get a lot of information from these packages. Now, we had talked about this database called Entres before, and I had shown you a little bit about it before. So I'm going to get sort of this utility subdirectory from Entres. And I'm going to run that. And then I'm going to open a connection. And what I'm going to do is I'm going to parse it. I'm going to parse, I'm just going through this quickly, but I'm going to do XML tree parse on this URL. And I'm going to start looking at things like children of the elements and so forth, XML children. And so I'm going to run this function. It says, if this is open, then you're going to run this. And I think it starts here and goes down to here. Hopefully this will run, yeah. And so what this did in Entres, this database, it actually, I'm printing out the first 5 databases that, I was trying to find all the databases that Entres has. And I'm just printing out the first 5. Notice that the first one is PubMed. So in other words, in this Entres database, it contains PubMed. It also contains a database called Protein. And it has a database called Nucleotide. So in other words, that's just the first 5. That's just the first 5 databases. Okay. Now there's another database called Biomart, and these are called, in fact at the med school they're building this MART database, and a student that took one of my courses a year or so ago is actually part of this team that's building this big database out at the med school. This is of course a national Biomart. It's sort of like a MART, M-A-R-T, like a food market, except that you go in and you shop for these biological databases and things. So the idea is how do you get information? Biomart is a query-oriented data system, and there's a package called Biomart with a capital R for R. That is the R implementation, which lets you access these biological databases. And so you simply just say library Biomart, and then I have head, and this is the first 6 that are represented. And then here's, for example, ensemble. And it tells you a little bit about these is a SNP database and functional genomic database and so forth. This is a fungi mart for fungi. If you're in a particular area of bioinformatics or in a particular area of biology, you're probably going to know where this data is stored or have some idea. As a statistician, you have the problem that you don't probably, so hopefully you're working with a biologist that knows where this is. Okay, so if I wanted to select this ensemble, suppose that's called a mart, so we want to select that. We could actually just say use mart ensemble, and then that brings it into R. So once you bring it into R, then I can list the data sets in it, for example, and in this case, I could list it. It's a 6. The dimension is 6 by 3, and so I'm not sure what would happen. How big is it? If I look at the environment. Yeah. Here it is. It's not so big. So at any rate. Now, suppose you want a data set suppose you want the data set on Homo sapiens. Well, who are the Homo sapiens? Us. And so this is a particular database, a gene database from Ensemble on Homo sapiens. So if you wanted to database the genes relating to us, you can get it. This is one way you can get it. And so, did I execute that yet? So if I execute that, then that should have appeared right here. Okay. And I commented that out, maybe because it's big. I'm not sure. You can play with it. I probably shouldn't play with it here. Anyway, if I want to, I can filter. I can do a summary filter of it. And doesn't have the function. Okay, yeah, these functions don't exist. I'm not sure why. These filters don't work. So these functions, probably what has happened is they've changed the name or they've redefined it or something, but they don't work. That's why he needs to update his book. So, at any rate. Well, I think I'll probably stop here. There's a small example here you can look at. And I did want to mention this GEO database because this GEO is a database for gene expression data. So we have a course on gene expression, and it does other things beside that, but this database has gene expression data in it. So you can go in and find some sample data sets that you could work with. So, and I won't go through this now, but the KEGG has been renamed and redone, so this code doesn't work. There's a keg.db, which even it has been superseded. So, at any rate, I'll stop here, and you can take a look at the last part. I may look at just a little bit more, but basically, if you're working in bioinformatics, you are going to want to go out and not only know where these databases are and what they are, but you have to be able to understand how to search the contents. And if you have a general idea of what the content is, then you're going to have to know how to extract the data from it. And the techniques I've been showing you is how you do it. The nice thing is, pretty much for the most part, you can do this all in R. Now, the NCBI, for example, has these web-based tools, but they also give you access to these databases directly, which is far better because it's much more powerful than trying to use a web interface. Okay, I hesitate to say, are there any questions, because I'm I'm sure for some of you this lecture kind of blew over top of you, but at any rate, if you get an appreciation for what you can do, at least I hope you have some appreciation that there are these huge databases out with all kinds of database information for biological sequence data, expression data, gene oncologies, protein-protein interactions, all this kind of stuff. These huge repositories in various places in the world. KEGG, for example, is a Kyoto. It's in Japan. And so, you know, all of these are out there. And if you're a biologist or you're a bioinformaticist, you have to know how to get it. You have to know how to pull this information and analyze it. So you have to use these types of tools. The nice thing is you can do it in R. Okay? Any questions? Okay.